So once again, as our remaining guests take their seat, I'm absolutely delighted to welcome so many of you here tonight. It's fantastic that so many of you have taken the time to see this presentation and hear from our speakers. The great news about tonight is that we also have, and I'd like to welcome our webinar audience of around 400 people who have registered to attend tonight's presentation from throughout Australia, and I noticed on the registration from beyond as well, which is great news. My name is Amanda Rogers, Corporate Engagement Manager at Engineers Australia. In keeping with tradition, I would also like to acknowledge the traditional owners of the land and pay respects to their elders. The format of tonight is that we will hear from two speakers who will then come together in a panel discussion, and then you will be able to ask questions. We've also, for our webinar audience, we have also lodged some of your questions that you put through when you registered, and we'll also be asking those, the most common ones that were put forward. It's been a very exciting series that we've partnered with Austral Masonry for this series, a long-standing partner of Engineers Australia, and we're very grateful for their support. This is the second in the series for retaining walls. Our first series was in November. We started off in Townsville, then we went to Brisbane, then Sydney and Melbourne, with over 2,000 people that supported that series. And again, we've retaining walls again with hydrostatic pressure component focus, and we've again broken that record for attendance. So it seems that this is a very critical issue and something that the engineering community are looking to hear more about, and for Engineers Australia to support you in that. I just want to talk a little bit about Austral Masonry. It's one of Australia's largest manufacturers in concrete masonry blocks, retaining walls, pavers and stone products. Austral's residential solutions can be seen on high-end architectural projects and landscaping designs, while their commercial solutions include coloured and standard masonry blocks, large-scale segmental block, retaining wall products, as well as a range of hard stand solutions such as commercial and permeable segmental block paving. Austral offer innovative solutions that provide structural integrity, excellent strength, durability and pride, and they pride themselves on making beautiful products that last forever. We have representation from Austral tonight, and I would encourage you to have a chat with them when we have the drinks and networking. Please make sure that your mobile phone is switched to silent. And without further ado, I'd like to introduce our first speaker, Chris Lyons. Chris is Associate Geotechnical Engineer for Arup. Chris has actually presented at all 4 of these series in the second series, so he's done a great job. He has over 20 years of experience covering the geotechnical design of various types of deep and shallow foundations, ground improvement, retaining walls and slope stabilisation works for both static and seismic loadings. His recent project works include proof engineering for multiple reinforced earth walls, up to 15 metres high, design of 23 metres deep fill embankments, and he is currently working on the design of deep station boxes, ground movement prediction and damage assessments for the Melbourne Metro project. Chris has been involved in all stages of project works, from investigations and detailed design through to construction, inspections and high-level project coordination. Chris also has several years of international experience, including working in the UK, New Zealand and the Gulf regions. I'd like you to join me in welcoming Chris. Thank you.
Thank you very much, Amanda, and thank you to Engineers Australia for helping to organise the series, and also Austral Masonry. It's been a bit of a tour going around. It's nice to kind of be back here in Melbourne to finish it off. So I'm Chris Lyons. I'm the geotechnical team leader here in Melbourne. Presentation tonight, as you all know, is on retaining wall failures and designing walls for hydrostatic pressure. And my talk tonight's going to cover some of the design aspects and also using case studies such as this, which is the Isle of Dogs Crossrail station in the UK. So using projects such as this, which I've worked on to kind of illustrate some of the design considerations. So my talk's in 3 sections. The first part is kind of defining hydrostatic pressures and design scenarios where the information we're going to talk about tonight could be relevant. The second part is failure mechanisms and some case studies of some jobs that have gone poorly. And the third one is designing to resist hydrostatic pressures and some case studies of jobs that have gone well. So hydrostatic pressures. So a definition would be the pressure exerted by a fluid at equilibrium at a given point within the fluid due to the force of gravity. So that's at equilibrium, which means that it's not changing. But of course, that's not always the case in the hydrostatic design we have to do. Quite often we've got dynamic water pressures, we've got moving water. And those can be just as problematic as actually just a hydrostatic water pressure. So it's not just fluid and equilibrium that we really need to consider. Hydrostatic pressure increases in proportion to the depth because of the increasing weight of fluid exerting downward force from above. So that makes sense. That's a nice kind of triangular pressure distribution, which we're all familiar with. But again, that's not always the case. A lot of times we've got confined aquifers or we've got flow nets going through the system, so it's not always a straightforward triangular distribution. So while we think about it in this kind of simplistic terms, it's actually quite complex. Controlling hydrostatic pressures will often be the most important assumption of the design of a retaining structure from Australian standards. So it's pretty important. It's key to get it right. A lot of the failures will predominantly be due to, or hydrostatic water pressures will have a key cause in it. So it's really important for our designs. And that's also supported by the UK guidance and the Syria guides. The assessment of groundwater pressures acting on walls is very important. So it's a key part of our design. So some design scenarios. So the talk tonight largely focuses on the pressure on the back of a retaining wall. But a lot of the ideas we talk about are equally applicable to assessing uplift pressure below retaining walls, which can give you a reduced sliding capacity beneath the wall. Uplift on basement base slabs, so it's the same sources of water coming in. Structural detailing for water tightness, and also hydrostatic pressure around tunnels or other buried structures. So while tonight's we're talking about retaining walls, there's lots of other design scenarios that the themes we're exploring tonight are also applicable. So things to consider. So design for the predicted long-term condition of the drainage system, not the as-completed system. Consider partial full blockage. So we're not designing for when we finish building the wall, it's how is the drainage system going to perform in 10, 50, 100 years' time? Is it going to clog up? Is it going to block? And those are the types of things we actually need to be designing for. So it's not the as-built condition, it's actually the long-term condition of our drainage system. Increased hydrostatic forces from a phreatic surface in the wedge behind the structure. So we may have a segmental wall, which is nice and dry on the inside, and we may have drainage behind that, but we've got a failure wedge coming in behind, and there's hydrostatic pressure sitting in that failure wedge because it's clay material. That's actually going to impact driving forces on our walls. So it's not just the drainage inside our wall we need to consider, it's also what's happening in the material behind the wall. And that goes on to the next point, water and tension cracks. Again, if we've got a tension crack behind our wall, that crack can fill up with water and you've got the full lateral pressure coming onto your wall. Other considerations, tidal conditions will change, or tidal changes, climate change, ground instability from piping or scour. So again, that's coming back to moving water and that can create issues with the stability of our walls. Drawdown effects, so it's not just the presence of water pressure, it's actually when we lose the water pressure, and that's one of my case studies later on. Chemical attack and how that moves with the water, and the removal of vegetation. So they're just some of the different things we need to consider when we talk about water pressures. So some examples of some failures due to hydrostatic pressures. I'd just like to say none of these jobs are mine. I've been involved in some of the reviews of them, but I'm quite happy to say that they haven't actually designed some of these projects. For curiosity, this is actually the Maya basement in Hobart, where they disturbed a buried rivulet, which then flooded their basement. But my first case study is actually in Dubai, so in 2008. So this was a, Just going back and getting my pointer going. Good. Yeah, this was a failure of a basement under construction. So a couple of things to talk about. The first thing was a diaphragm wall system, or they're called a slurry wall. So it's 800mm diaphragm wall. There's actually 3 walls in place. So you can see in the top right-hand photo, the front wall is the actual basement retention wall, which you can see in the during construction in the bottom photo. Behind that, about 8 to 10 metres behind, there was actually a quay wall. So that was holding back the main part of the water. In between the two, there was actually a culvert structure. So in the photo on the top right, you can see a bit of a dark patch at the edge of where the breaks occurred. So that's actually a vertical culvert riser, which I'll talk about in a bit more. There's 3 rows of ground anchors. And so in the photo down the bottom, they're actually excavating for the bottom row of ground anchors. They've installed the second row and they've installed the top row. But where that culvert riser was, they couldn't install the ground anchors. And again, I'll come back to that in a second. And then the third part of it is the culvert structure behind the wall, which is approximately where that zone A is on the photo on the bottom left. So then looking at the photo on the top right, we can see the front wall, which was the excavation wall, and behind that, this is during the failure, you can actually see the quay wall going in behind. You can also see on the very right-hand side of the photo, that's the culvert riser structure. Having a look at the plan down the bottom, the culvert riser structure is shown, and you can see they couldn't actually get ground anchors in where the culvert riser was going in, so they didn't have the top row of ground anchors. And what actually happened here was they constructed this slurry wall right up against that culvert riser structure. And they thought, oh, well, that's good. It's right up against the structure. We're not going to get any pressure on it. And they didn't design for any ground pressure or any hydrostatic pressure. But of course, as soon as the wall started to move, you started to get cracks forming between the two, and the water just pours on in. And it then starts to apply that hydrostatic pressure. So any crack you get, the hydrostatic pressure will get in there. The wall started to move. It didn't have a row of ground anchors, and the wall started to yield. That then proceeded to then force the anchors adjacent to it to also yield. That then resulted in those walls moving, the capping beam started to yield, and the whole thing came in. So just an example of making sure that your design's considering all the cases and watching out for water it will get into anywhere. The second case study is a segmental wall in China, and this was a large global stability failure which occurred pretty much straight after construction. And the key issue here was that it was poor backfill. It was a sandy clay material, both inside the wall and behind the wall. So they had some heavy rain events come through, and that just saturated everything. It saturated the wall itself and the fill behind, and it therefore became unstable. They didn't have an adequate drainage system behind, and they didn't have adequate drainage material actually in the wall, and that resulted in the failure. So watching out for the backfill material you've got inside your wall and also behind your wall. The third case study is the Orville Dam. So it's something fairly recent, or last year. So built in the 1960s, but they started to have cracks appearing in the spillway from 1968. And they were repeatedly patched, but water was repeatedly getting in. But water was known to come in through those cracks and to be continuously flowing underneath the spillway, which isn't great. And the issues were, the concrete was a bit inadequate, they didn't have adequate tie-down anchors, it was getting eroded, but one of the key parts was the rock was more erodible than they anticipated going through. And that therefore resulted in large-scale erosion and eventual instability, which nearly affected the whole dam. The key thing I take away from this is if you see a problem with water, deal with it, because chances are it's going to get worse. It's as simple as that. Water will be a problem. If you see anything which raises alarms, deal with it quickly. So a slight offshoot from hydrostatic pressures is dynamic water pressures. So this is a photo of the North Dock Quay Wall in Haiti from the earthquakes then in 2010. So with dynamic water pressures or dynamic effects, there's kind of 3 things going on. You may have liquefaction of the backfill behind, and this is an example of liquefaction behind the quay walls. But potentially you've also got a reduction in pressure outside your wall. So as the water moves away from your wall may become unstable and it may actually move forward. So that may have a destabilising effect. And that could be from a seismic event, or it could be a drawdown or a loss of water event. Similarly, if you've got water pressures coming in behind your wall, that may induce additional loading on the back of your wall. So that may be from some dynamic loading or from a seismic event. So anything in dynamic which could increase the water pressures behind your wall could impact on your wall. The fifth case study is a wall which I looked at a couple of years ago, and this was looking at the degradation of the wall. And so on the bottom photo there, you can see that there's been some, apologies, on the bottom photo there, there's been spalling of the front face, and that's gone about 30 or 40 mils back into the segmental blocks. And in the top photo there, you can see areas of discoloration and kind of this white powder coming down. So we had a look at this wall, and we tested the straps and we tested the blocks, and they were all good, all perfect. But then we tested the backfill behind, and we found that it had elevated levels of salts, so chlorides, sulfides, and calcium in the material. And what was happening was water was getting in behind in isolated locations. It was then just being naturally drawn to the front face of the wall, and as it was moving through the ground, it was picking up these salts. As it approached the front face of the wall, it would then evaporate, and the salts would then crystallise and expand, and they would then result in the front face of the concrete then spalling off. So this is just gradually occurring, gradually occurring. Was it a problem? No, not really. I mean, it's a degradation problem, but reinforced earth walls like these segmental walls are very good. If you lose a couple of blocks, you're not going to have a failure of the wall. You can go and repair them. So in the end, we haven't actually done any remedial works to this wall. It's more of a watch and see. However, if this was a reinforced concrete wall and you had that same migration of material going through and you're getting spalling, then you'd then be exposing your concrete and you might have more of an integrity problem on your hand. So those are my case studies of failure scenarios and some lessons learned. And the next part of my talk's about designing to resist hydrostatic pressures or groundwater pressures. So whenever I look at it, there's kind of three aspects which I think about. The first is to study the groundwater regime in the vicinity of the structure. So looking for sources of water, directions of water flows, seasonal tidal variations, understanding what your current groundwater situation is. So it's trying to collect whatever information you've got from historic boreholes. Are there regional borehole databases, either federal or state, that you can tap into, past jobs? So try and get as much information as you can to try and ascertain what your groundwater conditions are on your site. The next thing to think about is the chemical composition of the ground and the groundwater. So that's going to affect the long-term durability of your wall and how it's going to behave. And then the third part, which I always think about, is the effect of the proposed retaining structure on the existing groundwater regime. So for instance, if you're putting a cut-off wall in, are you going to restrict the groundwater flow? A deep basement could actually, if you've got a flowing groundwater and you put a deep basement in, that actually could create a mounding of groundwater on one side, and then on the other side you might actually get a drawdown as the groundwater flow moves around your deep basement. Again, if you're putting cuts or excavations into the ground, are you going to be lowering down the groundwater table? So that's what I always think about, these three components. Understand what you've got in terms of a groundwater regime, think about the chemical or the long-term degradation of the wall, and then think about what's your structure going to do to change the groundwater regime. So having a look at some design codes. So AS 1170, so a common code. So it effectively says that you can take groundwater, either assume it's at the ground level or at a level with an annual probability of exceedance of 1 in 50. So, you've got to try and work that out. Chances are you've only got a couple of boreholes from, maybe a month's worth of monitoring. So to try and work out what a 1 in 50 exceedance is can be pretty tough. So quite often you're left with that first one. You then take those hydrostatic pressures and it would then say to put a factor of 1.2 potentially on those pressures for a design of a structure. AS 4678, earth retaining structures. So that talks about design on a worst credible water level for the strength and stability case. So a different type of water table to AS 1170, but you then use a load factor of 1 instead of 1.2. So two different codes are talking about two different ways of assessing your design groundwater profile and then two different ways of factoring it into your design. So they're not strictly compatible, and you've also got to watch swapping between your codes. AS 5100. Again, something different, a 1 in 100 year water table for SLS and a 1 in 1,000 water table for ULS. So a different approach again. Looking overseas, C760. So it's a section 5.6 on groundwater. It talks about a most unfavourable value under normal conditions, as an SLS case, i.e. over the life of the structure, again the long term, how do you think the wall's going to behave? And what do you think would be a reasonable design level for that? And then take an extreme or accidental groundwater level, so i.e. a pipe burst or an extreme flood event. And checking that your wall then has a ULS stability, i.e. you won't get a wall failure. Figure 7.4 actually has a very good diagram for considering the different inputs on what you might take for a design groundwater table. But it also goes to say that this code, or the standard, typically talks about braced excavations for basements, where you then typically put in a reinforced concrete structure and you have the whole thing propped. And therefore, in the long term, groundwater is not such a problem. So therefore, you got to think, again, are these necessarily applicable to an above ground retaining wall? Maybe, maybe not. So again, it's how the code's intended to be used that you need to consider. And the last one, BS 8102, protection of below ground structures. So it talks for basements below 4 metres deep, then you should take a groundwater table as 1 metre below ground level. So there's lots of different codes out there, lots of different ways of looking at it, and they also treat the groundwater design in different ways. So there's a bit of a match. You need to be thinking carefully about the design code you're using. From AS 4678, there's some typical details in the back there. There's a whole range for different types of walls. So this is a good place to look for examples on what you should be thinking about for drainage designs. But I think my caution would be, don't just take these and copy them. Think about them and think about how they apply to your job, because they're different for each case. Just looking at them for a wee bit. So the one on the left, so this is a reinforced earth wall. So key things are they've got a back slope coming down, and then they've got a channel in behind the wall. So what they're trying to do there is divert the water away from the wall. Try and get rid of the water if you can. They've then got a granular fill material. So okay, so the water's going to come into the wall behind. It's then going to drain away very quickly. So I'm not going to build up large amounts of hydrostatic pressure behind my wall. And in this case, they've then also got a geofabric or drainage layer going down the back of the wall and underneath. And this is based on having quite high inflows or expected inflows into their wall. Reinforced earth walls are nice and permeable typically, so the water can normally flow through the front face, and they're normally segmental on the front blocks. So in this case, you don't need any weep holes, and the water can typically move towards the front face. But also watch out at the toe of the wall there too. You don't want to be concentrating all the wall at the toe of your wall, because if you're in a reactive basaltic clay, for instance, you're going to cause that ground to soften. So it's not just get rid of it in front of your wall, you also got to think about where it's going to go to. The diagram on the right is for a reinforced concrete wall, stem wall, and a couple of different approaches. So this time, they've got a drainage channel at the top, but they've then got a clay plug over the top of the wall. So this is saying what we're trying to do is prevent the water coming into the backfill and into the fill behind our wall. So again, trying to get rid of it before it affects your stability. They have to have weep holes because no concrete wall won't allow water to drain through, so that's another consideration. And they're a pretty cheap way to mitigate your risk against groundwater in your structures. And then a lot of the other ideas are pretty similar. So AS 4678's got some good details. And then in terms of mitigating pressures, so the things I think about, first, try not to deal with the water, try and get rid of it. Try to divert the surface water away from the drainage. Avoid any ponding, avoid any low spots. Make sure you've got falls going across your wall. A typical details is provide a 300 to 500 mil thick clay seal above, and again, that stops the water permeating in. I've had a question about that shrinking and swelling, over summertime, and that may shrink and swell over summertime, and therefore you might get some cracks in it. You might get a bit of water come in as you get first rainfalls, but then that'll just then expand and swell as you start to come into your wet seasons. But try and put a clay layer in to stop the water getting into your wall. So wall drainage, so subsurface drains, weep holes are cheap, filters and geotextiles, thinking about your fill materials and potentially the grading between your fill materials. You don't want to have clays moving through more granular material and potentially clogging up your drainage system. Drains potentially designed to AS 3500 and 2439, so at least you want to specify the size, the class, the type, and the joints of the drainage. And monitoring and warning systems, think about how you can mitigate the risk. So for basements before, I've had weep holes come into my basement, so if I did have an elevated water pressure coming up, water would start to come into my basement, and it would then start to activate the drainage system or the pump system. So instead of your pumps going on just occasionally, they're then starting to go regularly, and that tells you the groundwater level is starting to rise. But some things to watch out for. So crushing of geocomposite drains, so 4 metres of fill. So that's where it's potentially important to be specifying the class and the type of the material. If your drainage gets crushed, then it's not going to do you much good. Hydrophobic geofabrics. So these types of geofabrics will induce surface tension. So until they're saturated, water actually sheds off them, so it won't necessarily pass through. Reactive soils, I've seen walls burst open, not from the hydrostatic pressure, but from the expansion of the reactive soils behind. Or clogging of geofabrics and fine soils. So even though you've got a geofabric, it doesn't mean you're sorted. You can still have clay or silt material come in and clog up those geofabrics. So you might need a sand layer in between to help mitigate that risk for the long-term performance of your structure. So some case studies. So my first one is the Isle of Dogs Crossrail Station, which I was the lead geotech engineer for in the UK. So this was constructed in the middle of the docks out at Canary Wharf in London. So we kind of used 3 retention solutions on this wall to resist groundwater. So the piles on the right there, adjacent to the box, the darker ones are actually tubular steel piles interlocking together. So that's providing a completely watertight or hydrostatic resisting boundary. Below that, we then drilled through with concrete piles to create a contig wall. So that had gaps between it, so the water could then flow through, so a cheaper solution. And on the other side of the wall, we then, in the top part, we had secant pile walls, so board piles locked together, again to provide a watertight seal. But then down the bottom part of the wall, we stopped every second pile. So again, we went to a contig piled solution where water could come through. So looking for some of the rationale for this, this is the design hydrostatic pressures we had to deal with. So on the left there, we've got the pre-construction, we've then got the during construction, and then long-term conditions. So looking at the pre-construction, so the groundwater level on the dock was about RL 105, and then we had about 10 metres of dock water, which we had to resist. So that was a direct hydrostatic pressure on our walls. We then came into an aquifer layer, the Harwich Formation, and we then hit the Lambeth bed, which was an aqualude. And that was preventing the direct transmission of the groundwater head between the upper aquifer and the lower aquifer, which was a sand layer. So that's the change in the existing groundwater profile. And this had occurred because over the years London had been dewatered. So therefore the lower aquifer was suppressed. But if you look at the long-term condition, that water pressure in the lower aquifer has popped right up. And that's because they can't dewater anymore. So therefore there's a change in groundwater pressure. So it's not what your groundwater regime is on the day you finish your job, but what it's going to be in 50 years' time or 100 years' time. During construction, the middle photo there, we actually dewatered that whole lower aquifer. So therefore that's how we could get away with contig walls, because we didn't have to deal with groundwater coming in. So that was a cost saving. But the other point was because we were in docks, we had this 10 metres of dock hydrostatic water pressure, but there's a chance that the dock walls could fail somewhere else. So therefore we could actually lose that whole 10 metres of water on the back of our wall. So we had to make sure that our wall is actually stable, not just with the 10 metres of water on it, but also if we lost that 10 metres of water pressure, that our wall wouldn't fail in the other manner. So it's not just designing for your hydrostatic pressure, it's potentially designing for the loss of it or the absence of it. So the construction sequencing, so we did steel tubular piles by the Geiken method. We then drilled concrete board piles through those. We connected them together to then provide a construction deck, and we then dewatered the inner dock. From there, we could then construct the secant pile wall on the other side. We then put in tension piles, because of course we had about 240 kPa of uplift pressure on the base slab of the station, and we then did a bottom-down, a top-down construction methodology. And this was the Geiken pile installation method. So this is a Preston piling method because all the buildings around were filled with accountants and lawyers and bankers, and it was a lot of important people with a lot of money. So we made sure that we were minimising any disturbance to the local environments. Yeah, this machine could then go out over the water and sequentially press in piles to then construct the perimeter wall, which we could then dewater inside. And this is just a detail of their customised clutch. So we had the large steel piles with 2 C connections, and they then had little bit grout socks, which they put in between those connections and then grouted up to provide the watertight seal, and that worked pretty well. So finally, just a couple of other case studies. So this was a job in New Zealand actually. So this was using soil mixed walls to resist water pressure. So this was resisting about 3 metres of groundwater pressure. No drainage system at all, just retaining the full water pressure. And, those soil mixed columns work pretty well in terms of a temporary solution to restrict groundwater flow in. The second one is a reinforced earth wall in Tasmania. And so this was constructed above the ground surface level, so we weren't necessarily interfering with the groundwater. It was out of a 1 in 100-year flood zone, so a low risk from floodwater. The reinforced earth wall was granular, and the backfill behind was also very granular and of a similar grading. So there wasn't a large risk of migration of material and if water got in, it would dissipate away quite easily. So in the end, we actually just put a slotted drain coil with a bit of filter fabric around it, and that was our drainage system. So a relatively significant structure has got a pretty simple drainage system because considering it, we think was a pretty low risk that we're going to have issues with our drainage. This wall here, however, was constructed in erodible Lewis material. And so we're really concerned about the water here. We put a concrete channel behind the wall to divert the groundwater flows away. There was granular backfill behind the wall, wrapped in the filter fabric, and that then had a slotted sock down the bottom. That a slotted drain coil. That drain coil then sat in a concrete channel, and the whole reason for that was we didn't want the water just to come in behind our wall and sit there, because it could then saturate or erode underneath. We wanted to come into our wall and then go along that concrete channel and then be taken away. And so we were then taking that away to a sump, which is then constructed at the end of the wall. And that then also diverted off the property, so we didn't just have a discharge onto the ground surface, which could then cause erosion. So in the end, we spent more time designing the drainage for this wall than we did the actual wall. Drainage was a key factor of here, and we put a lot of effort into it. So it's horses for courses. And that's my presentation. Thank you.
Thank you, Chris, for that. I'd now like to introduce our second and final speaker for this evening, Dr. Jim Yang. Dr. Yang is Regional Director of Geotechnics and Tunnelling for the Australian region of Arcadis. He has responsibilities that include team leadership and the technical delivery of all major projects. Since joining Arcadis, Jim has built the geotechnical and tunnelling team into a group that can provide full geotechnical and specialist tunnelling services from site investigation through to detailed design. Jim is a chartered professional engineer with over 25 years' experience in project management and design of infrastructure and building structures within Australia and overseas. He has published over 50 technical papers and invited lectures. Jim was the co-chairman for the China Tunnel and Bridge Summit in 2012, 2016 and 2018. Please join me in welcoming Jim. Thank you.
Good evening. Thanks, Amanda. The topic has been chosen basically, but my focus on tonight's talk is about, why water pressure is critical and how we manage it on a day-to-day or get the most people we have to deal with. So I'm thinking about, what I should talk about. So we probably, when we design something, we've got to have a code of practice. So then I have a bit of review. What's the current code practice? All guidelines we have to consider. And I'm going to talk about real, wall, I'll put a quotation mark there, collapse of a retaining wall or deep excavation due to a waterman burst. That's about 10 years ago. And I'm going to show you some of the real example projects I personally involved to show or share the knowledge of how we manage the groundwater issues for various projects. So the first one, this one is get from the internet. Essentially, in 2004, probably Nickel Highway, most people would have noted that from the website. But the thing was that 4 people killed, and it had become a very big issue. I just listed this is nothing new. Oops. Trying to see the pointer. Oh, not working. Is it? Oh, no, the other one, sorry. Okay. So actually there was a design error through the inquiries discovered. And one of the things was the use of plexus. I think it's been very popular in our geotech industry, and how you use correctly is very important. So retaining wall code. I'm more of age, I suppose. I went through the working stress times, user factor safety, reduction factor or material factor apply on the material and so forth. So to me anyway, I feel much easier. However, in today's codes, I'll list a few. You have to follow the ultimate limit state code. So you've got to consider the load factors on it. And the material factor depends on which code you're looking at. And any designer is required to look at both serviceability limit state, which is for deformation checks, under various conditions, and also ultimate limit state case to make sure in the event of that ultimate condition occur, your structure is not going to collapse. So looking at the code, okay, in general, I think the loads can be considered in three sort of categories. One is the data load, going to be forever. And this one is like a small block wall, You still need to consider all these data load, potential life load, because there is a traffic going to come along, and of course water. And that's the focus of tonight. But whether the water going to be changed with time and so forth. And for some regions, you're going to consider earthquake loads, train loading. These are transients or potentially extreme conditions. So what are the load factors? You're going to consider different codes, ask you to follow different sort of design philosophy. But within Australia, we got bridge code, most people follow, S5100, and also retaining wall code S4678. Now, you'll probably be aware of 4678. In the introduction, it says the walls no more than 50 meters, you consider. So you've got to be careful when you apply. So I just put in there that this is more based on the bridge code. So your basic material factor, you've got to, for if it's in your favor, you'll actually factor down. But if it's on the driving side, then you actually factor up. Now, in particular, with respect to water, it depends on what you look at. If you look at a worst case scenario, you can use 1. But some other cases, there is a bit of a debate. I think in the industry, it depends on your interpretation of the code, how you apply for it. Sometimes, probably for some jobs, you don't know. We don't know actually what's the criteria, and there is no design brief. What do you do? So we probably have to exercise our engineering judgment or make up our own criteria. I'll show you this because this one is in the commentary. Actually, the bridge code actually follows. It's got 2 branches. One is actually in situation that probably more on the case I'm showing here, like a typical crash barrier. Your soil load is very small, but the impact load on that little airship retaining wall is governing case. So you go follow the left-hand side branch because it's more structural governed. However, most of the cases going to go to the right-hand side approach where the soil water pressure is governed. So more like a geotechnical design case is governing. And we can use, I call fudged working stress method because you actually can apply the normal serviceability conditions. Then once you got all the design actions, all you need to do is to factor up by factor 1.5. So in that way, that you actually now factor down the material factor, and kind of easier to understand what's the actual behavior of the soil and the water in relation to the retaining system. Now, I'll put this up, actually, I presented back in Sydney's symposium, why water is so important. And just look at these 2 cases. That's water table there, so that's only, soil pressure acting on the wall. But when you look at this case, I'm just trying to draw in a proportion. So water pressure is about 3 times as compared to the soil pressure. So hence, always got to remember, when you design a retaining wall, if you don't consider water, and when the water table rises, your wall is going to collapse or fail, whichever way you're looking at. And then when you're looking at, say, this is a station box, this is a top secret job we're working on at the moment. I wouldn't mention name, but very close to sea or bay. Well, what's the groundwater regime looks like? You've got to look at a temporary excavation condition and a long-term condition. Look at the durability aspects of the groundwater because you're close to sea. And potentially, if you do a station box, well, it depends on where the water flowing. Is there going to be a dam effect, i.e. one side of water will be higher than the other side? Look at the geometry of your structure. You may have an unbalanced water pressure and soil pressure as well. So the other case is that the next thing I'm going to talk about, when you design a station box structure, like a Melbourne Metro we're working on at the moment, well, what about the breakage of any water mains, or gas main, and so forth? What's the impact? And then that's sort of the interaction we really need to look into it to make sure that when we design these, they're all safe and sound. So I'll just look around. I mean, this is just a bit of summary of different codes with respect to water main breakage. So look at the Australian Bridge Code. It actually didn't talk about exactly whether you consider or not consider, but it says along the line, you've got to consider 1 in 2,000 return period. Well, that's very, very high. Water table can be built up behind your wall. And then look at the British Code, BSS 1002/94. It actually clearly says, well, you've got to consider give rise to changes in the long-term groundwater. So when you design a retaining system, you're not going to design for tomorrow. Actually looking at, depends on the design life, 30 years or 50 years or 100 years or beyond. Sometimes the lawyers love to extend the case to 120 years so far. In some cases, 150 years. Gee, I don't think any engineer can live that long anyway. Look at Hong Kong's Geo Guide for deep excavation consideration. And probably the one with the clearest sort of indication in situations where significant water flow can occur in event of breakage of a water main. So it's very clear, you have to consider that. And AS 4678, it actually asks us to look at a range of factors, water flow and so forth, but it highlighted that the effect of water discharge from any drain, pipes, and the like on site should be considered. What that mean? Consider for 1 year or 10 year or what event? It just stopped there. So it has left it to us for interpretation and judgment. And the serial report C58, again, look at the serviceability and also the long-term or short-term, long-term. Very similar. The more recent, the Euro Code, it's very clearly specified. The failure of a drainage system must be considered as an event. So I'm going to play a video. So this is about more than 10 years ago. I've got a phone call from an insurance company. There was a water main burst on Botany Road in Sydney. Can you come around and have a look? So the main was 450 millimeters, and the wall moved 75 millimeters. And the road was closed for about 3 months, and they got a purpose at the burst end of this area, and the entire work was delayed by 6 months for remedial work and huge claims. And all the parties involved, including City Water, was invited, and that's the consequences when water main burst. And it's all flooded later on, and water just spills through it. I'm going to talk about it a bit more because this second part will actually through the sand layer. So once the water main bursts, you fill up the water quite quickly. Okay, just stop there. And that's the consequences of full of water of the pit. However, I think the beauty of geotech, when there is a problem, we use the dirt to fix it. We build a berm, after the wall was declared unsafe, and then we deal with it later. So when we look at it, This is the project site. So this is the wall, about 50 odd meters, and that's Bottom Road. And the green is the perimeter wall. It's a quite large excavation, and the pipe burst was along there. And it was second power. It meant to be pretty much waterproof, and it's true. That's the intention, you know. The original design intent, it's a very dry excavation, everything's happy. And what's interesting when you look at the report, original design report, piling code, concrete code, BS code, British code, serial report, Euro code, all referred. You know, what's more interesting, the code of practice, I saw some people in the audience, you know, got some gray hairs. I'm sure heard of a CP2, which was 1951. And that was the basis of the design with a factor safety of 1.5. So when you review that report, what do you think? Why the others hasn't been considered for the current ultimately mistake design? So this is a plot trying to look at. So that's the wall, and the base of excavation is about IS7, and the top of the wall sort of stepped with a cabin bin there. And they got 2 levels of anchor. The piles was second pile was 600 meter diameter, and these anchors are pre-stressed at a different load. But what's happening is, you see, you got this loose end, which is perfect medium when there is waterman burst, because the water can travel through loose end very, very quickly. And when you look at it, the original design intent, say, okay, got 2 levels. That's soil anchor, and the low anchor trying to socket into rock, or that's very weak. And the design water table was about 9.5 or 10 or whatever. So you can see that's excavation, and that's the net water pressure. See, it's tiny, yeah, not much. Although we know it's governed in the design, but when you look at the soil, plus a bit of traffic on there, however, when a water main bursts somewhere here, water fill up, your water pressure is increased by quite a number of times. And the wall has been pushed over about 75. So, okay, when we look at a case, well, let's do some back analysis. They're using the same thing. They use a Wallop program. And when you look at it and trying to simulate the work, what are going to happen if I raise the water table? And actually, it's amazing, actually. We didn't change anything, but in order to get the numbers, you know, the movement sort of the wall, same as what has been measured, and you can see the design actions a lot higher. It's very interesting. And of course, the designer would have declared, say, that the wall wasn't unsafe in that circumstance, which is fair enough. So what has been discovered? I think it's a lessons takeaway. See, if you haven't used these codes in your design, please don't quote it. What do you mean? You quote all these references, but you never use it. There is no context of using it. And the presence of loose to medium sand near the surface or near the pipe, you know, that's perfect opportunity for the pipe. When it's burst, get the water, charge up, push your retaining wall. And the original dam effect wasn't considered, because when we look at the development, it's a quite a significant area, and the water actually was flowing towards the wall. So the water table actually, when we put a piezometer there, actually water table is higher than the original. Again, the overdigger wasn't considered as the per code requirement, but on the hindsight, it was actually requested by contractor, well, cannot get away without the over excavation consideration. And then, you know, the engineer always be nice people. Yeah, okay, if you control and do the survey properly, you can go ahead. So the safety margin being taken away, see, when you look at the multiple factors as you go along. And the other thing is the interaction of the ground anchors because original was 2 parallel, but then they sort of, overlapping in terms of wedge pull out. And the other thing we discovered is the interface between structure engineering geotech wasn't clearly defined as to, well, once you've got some action, what do you do, the design and so forth. And then there was a remedial work, of course, after the berm was put in place, and there were additional anchors put in place. And at this time, lessons learned, all the anchors in rock. So it doesn't matter if your water level-wise got plenty of reserve capacity. And what's even more interesting, just show you the well size, original design there. This is remedial works. And I'm sure I can slip away on that one. So now, the next a few slides, I'm going to talk about some of the real projects I involved in the past years. This is for reinforced soil wall. Austral asked me to say, well, talk about that. So this is in New South Wales. In New South Wales, when we design reinforced soil walls, we can't get away or deviate from it. The R57 code requires that for the reinforced soil block, we must have a chimney drain of 300 millimeters behind it. On top of it, we have to have a kind of a barrier to make sure no infiltration water pressure, because it's a priority system, and you must design or make sure got lower permeability layer to ensure no infiltration or very little infiltration towards the reinforced soil block. And however, there is a requirement, interesting, says, while the reinforced soil block itself going to be designed, the specialist company, the geotech need to look after bearing, sliding, global stability. And one of the other cases we have to do is to consider the water pressure, the water table is actually near the ground surface in front of the reinforced soil block. But for this particular case, because it's a relatively weak material behind it, and we found we have to extend this reinforced soil wall further back to achieve the global stability requirement. And this is a pumping station for Eastern Distributor in Sydney. That's the first toll road and the tunnel project constructed in Sydney, actually. It's a road tunnel. But this one is the pumping station. So what do we discover, actually? When we did a few boreholes, we found interlayered aquifer and aquatar when we put a piezometers in there. So how we deal with this? So when you design a box structure, essentially, 12-meter diameter and 60-meter excavation. Well, what's the mechanism? And then what's more interesting, actually, that's all I learned when we drilled 4 boreholes around the perimeter. And you can't do cross-sections because it's very valuable, actually, amazingly. So we need to look at, well, if the base is sandy soil, well, could it be pumping issues when you excavate down, remove the overburden? But if it's more clay soil, you can have a base key failure mechanism to occur. So we end up actually use of concrete plugs at the base. That's for use for construction. And for the permanent works, we put a tension ground anchors socket into rock to deal with the long-term uplift. And I was fortunate, I suppose, to work on the Bangkok Metro. That's the first metro. What I'm talking about is nearly 20 years ago stuff. And we have to design this retaining wall. In those days, we used wallop. But what's happened is the groundwater actually originally, it's like this shape, and due to the pumping of that sand layer over many, many years. However, there's also a requirement. We have to consider the flotation when the water table restore, like same as the blue one. So when you look at 30-meter excavation for station box, it's a very significant uplift. So we use a tension pin pass to resist that. That's like 60 meters from my memory. And of course, we consider the toe kick out and so forth to look at the different water pressure conditions. This is, again, Bergman's station. That's again the first metro. This is more than 10 years ago as well. Was fortunately involved in that. And this station is the interchange of a green and red line. The station excavation is about 30 meters depth. And they like to, because Dubai is very hot, so they like to get all these perimeter sort of excavations for shopping mall. So you can get in there quite cool, because in summer it can get over 50 degrees. The geology over there is mainly sand, and the water table is quite high, but the rock itself actually quite highly permeable. If you look at permeability, it's similar to sand. So we have a diaphragm wall system, and to the depth such that during excavation we're going to have good control of water inflows and make sure it's in dry condition. And of course, long term, we have to do the flotation and tension. We use diaphragm wall breadth. And what's more interesting, actually, probably not so much with water or hydrostatic pressure, we almost finished the design, and they said, oh, by the way, actually there is a viaduct going through that, sitting on top of it. Anyway, so make it more interesting. But what I want to highlight here, actually, 10 years ago, we tried to do the 3D. We did it in terms of the presentation and plots, look at the details. But in terms of modeling, we use the plastic, but the capability in that time wasn't as good as today. Computer was much slower. It takes us actually days to run such a large model. So we decided to use 2D and lots of interaction with structure guys to come up a proper solution. And I dare to say, so far, no news heard from the Dubai Metro thing, so it must be performing okay after 10 years. This more recent ones, the first segment of Sydney Metro called Northwest, and the name has been changed along the way. And this is the Castle Hill station. What I was involved was temporary works, and there was some fault zones identified. Initially, actually, the fault zone actually going underneath the excavation, so we thought that wasn't an issue. You know, we don't need to worry about too much when you look at three-dimensional. And however, during construction phase, when they install in kilometers and did additional boreholes, they have discovered, oh, actually this fault zone is much shallower. What I'm showing here, that's still 20 plus meters depth. So you imagine we originally used ground anchors trying to tie the back for stability, but when you got a wedge, we never considered what do we have to do. And potentially there was some leakage, water main there. In the end, we put some additional rock anchors there, but what I'm trying to show is actually we use some subsoil drains to make sure, well, in event something happen, we still can manage the water pressure rather than building up a lot. So what's the takeaway from my presentations? I suppose it's very important to recognize how important the water pressure is in relation to retaining system design. Doesn't matter it's a shallow wall or deep excavation or whatever. And be careful when you look at a code of practice, right? Just to go to not only look at one clause, you really need to get a full understanding what's the context of the code when you select the material property or load factors and so forth. So for deep excavation, I suppose, we got to check the lateral stability under different load conditions, vertical stability, and both short-term and long-term conditions, including water table changes with time. And if you deal with deep excavations in clay soil, got to check the base heave failures. One of the things that I mentioned at the pumping station, actually another pumping station for Eastern region construction was in sand, and you usually have for the durations you have a backup. However, when the first pump failed, the backup didn't kick in, so there was a significant failure. So it does happen when, some of the sort of systems fail, I suppose. And for sandy soils, you've got to consider the piping failure mechanism. And for the permanent structures, if it's tanked, you've got to consider flotation. And I think I highlighted enough. When you're designing deep excavation or retaining walls, if there is a water main behind it, you've got to make sure you investigate thoroughly to ensure get approval from the authority. Otherwise, you'll consider as an ultimate limit case to make sure you're not going to have any issue. I just listed these, all the cases I present tonight, except the first slide from Singapore. It's all from my past published papers. And since I talked about a legal case, I just want to make a disclaimer. This is my personal opinion, not representing Arcadis / for the previous company, or Arcada. And I also want to express my gratitude to my many former colleagues, or the current colleagues. They helped me a lot in implement these projects. Without their support, I wouldn't be able to do this presentation. Thank you for your attention.
Thank you, Jim, for that presentation. Just going back to the format of tonight, so I'd now like to invite both our speakers to sit up here and form a panel. I'd like you to start thinking about questions that you may have. We did take some questions from our audience, particularly our webinar audience tonight. So while our speakers are going up there, I'll kick off with a question that we received, and there was quite a there were a lot of questions around climate change with hydrostatic pressure, and the questions that we had, if we sort of like consolidated all that, is that do you have any comments or thoughts about on the impacts of rising sea levels and related hydrostatic pressure changes expected over time?
Okay.
So Chris, maybe you can start with that one.
Yep. Yeah, I think you've got to look at the long-term considerations of the wall, so and climate change and rising groundwater levels are a key part of that. There's a lot of published information out there, but again, it can give variable numbers. So you've got to kind of wade through that a bit and decipher what you think, say, a reasonable number to be using. If you're retaining walls out by the sea, then okay, you can kind of get a decent idea on what you should be using in terms of an increase by looking at that documentation. However, if your walls then ensure, 200 metres, 500 metres, a couple of kilometres, there's then probably a question about how much that seawater levels rise is actually going to affect your wall. So again, you've got a bit of a judgment call to make there. A conservative way to do it would be just you just take the whole thing. If you're talking about 100 mils or 200 mils in your groundwater table difference, then you might argue the point. Groundwater is an issue. You don't want to push it too much.
I'll probably just add a couple of comments on that. I think the crystals that you mentioned depends on where you are. I suppose whether it's coastal development or not. But I think the other factor is that the natural water table also going to be fluctuate with, due to different rainfall events. And when you look at really heavy rainfall events, the water table can rise 1 to 2 meters. So that's probably even higher than these sea level changes, what you're looking at. So it is worthwhile to look at, what's your PMF sort of flow conditions. And for instance, we're doing Sydney Metro, the second phase in the CBD area. Certainly that's one of the requirements has been written into the project brief, and then we have to investigate that.
Okay, so I'd now like to invite a question from the floor. If you do have a question, Florence, my colleague, has a roving microphone. Just put your hand up. Could you just say who you are and where you're from, and just direct your question to the panel? This gentleman up in the auditorium part of the, the room.
I'm Ranjan Fernando. I'm working for my own practice. I would like to raise a question for Dr. Yang. I would be happy if you can show me the slide where you have done a deep excavation for 30 meters in Bangkok, so that I can refresh and raise your question. A slide that you have done some deep excavation using Wallop program in Bangkok.
We use the Wallop.
Yes, I just want to see that slide. Can you just show me the slide, please?
Okay. Yeah.
Yes, okay. Is it 30 meter deep excavation, right?
Yeah, it's roughly 30 meters.
I do not know your piles and all that, but I'm a little bit concerned about your support condition, and I can see you use some moment stiffness where the arrow with some mark between your support condition. So I just would like to know what does that represent in addition to the final condition with slab support in the wall. I can see some marks in between, so I just would like to learn about what is that and for what purpose you have used these support conditions to simulate your structure.
Get a pointer.
Thank you.
Yeah, I think my apologies first of all, actually, because I actually just extracted my picture, and so you're talking about these stuff. That's just the original was like some detailed levels of the geotech profile. Is that something you refer to? You mean these?
In between your prop support.
These?
Yes, what is that?
Oh, these are the levels. The ground levels? Yeah, I just said, my apologies because this is from my paper 20 years ago, so I just pulled it out. Stuck in here, sorry about that. Yeah.
Thank you.
I guess you can't see from that far, that's all. Yeah.
Could I invite another question from the floor? This gentleman here with the blue shirt, thank you.
Hi, Don Reesbeck, retired Principal Geotech Engineer. One area...
It is.
Hi. One critical area is sloping sites where you've got a hilly site where you put a reinforced wall in, and a lot of, say, a forward pier wall has thin drainage between the piers, and it's quite often that you get a spring emanating from uphill, which produces very high water pressures, and often the sort of geotechnical drainage behind the retaining wall is very minimal and can't take those pressures. And it's a bit like the water main bursting. You can actually, under a clay layer, say in between clay and rock interface, you can get a flow in between the interface that's quite high, and it can actually, in the natural situation, can burst out of the ground because of the head up the slope. How would you overcome that in a retaining wall design?
I can come first.
Sure. Yeah, I think the first thing is to understand what your groundwater regime is there. So as you said, you've got a sloping site potentially, and potentially you've got clay layers on there. So you've got to think, well, are they going to behave? Well, are they going to retain the water, or are you going to get perched water tables as a result? So I think, yeah, understanding what your ground conditions are. And then the third part I was looking at was, what's the influence of your wall? So sure, you've got drainage in behind your wall, and that may draw it down, but are you necessarily going to draw all those layers down? In terms of, it's always hard to know if you have got a spring back there or not. I think it's a judgment call, and I'd be looking at thinking about drained or undrained behaviour of my soil layers if I've got clayers on there. And then I think construction supervision in terms of seeing what's actually occurring. If you do see you're getting a lot of flow coming into your wall, then you need to be checking that your design's actually accommodated that.
Often during the investigation, it doesn't show up as a major pressure, but it tends to be intermittent during heavy rain. So you get
Yeah, and so again, I think I like that serial guidance approach where you design for what you think is a reasonable case, but you then check for the extreme case. So I think if you're checking for something like a burst water pipe or an elevated water pressure in behind, then yeah, you might get some additional movement if that does occur, but you shouldn't hopefully get a failure. That's the intention. So again, that's where monitoring comes into it too. So if that is occurring, you'd see some movement, and that may also trigger you to look a bit closer and additional rows of anchors.
Thank you for that. Can I invite the audience another question? Thank you. If you just sort of state your name and where you're from. Thank you.
Hi, Chris. Jawad from EIC.
Hey, Jawad.
Just, I want to get your thoughts on composite walls, where you have an external, for example, soldier pile wall, and you have internal box structure, and commonly for metro stations and underground stations and the like. The external pile wall is usually designed to enable the construction of the box structure, and then the internal box structure is designed to take the water pressure in the long term. But the box structure is cast against the external wall. That's how they're built. How do you ensure that they actually work independently and they're not bonded together, and then that they actually behave the way they're intended to?
I'll go.
You go
I'll
first.
go. Yeah, sure.
I'll probably have
So
some thoughts as well.
I think you want to be thinking about your water membrane systems. So British standards would say that you probably need potentially two barrier systems to have a fully watertight solution. So therefore you may potentially have a membrane liner in between your retention piles and your lining wall. So that would provide a natural mechanism for the two of them to come apart. I think you also want to think about what your groundwater is doing when you excavate down, and if you're in like a rock formation where it's going to be drained behind your wall, then you'll be putting your retention piles in, you'll then be casting your box. But then when you put your hydrostatic water pressure back on, all your water pressure is going to come onto your lining wall, so potentially that's going to move in, and then it may actually move away from your retention piles. So yeah, there's a few intricacies going on in that type of situation in terms of the movement of the two walls. Yeah, so it's a bit of assessment and I think modelling to try and fully realise what's going on.
I just want to add some comments there. See, first of all, I think conceptually you've got to look at, is it a tank structure or going to be drainage structure? So this is fundamental. You see, if you're going to design a drainage structure, and then you need to have a drainage system behind your box. However, if you use a membrane and it's a tank structure, that means you've got to deal with the full hydrostatic pressure, which may experience by the box structure. And the current practice is basically, or the common understanding among the engineers, there is no waterproof membrane going to have 100% security to seal off all the water, i.e. if you put in there, there will be leakages and so forth. So that's very important to recognize. We spoke to so many suppliers of waterproof membrane guys. They can't give you 100% guarantee.
I'd like to just interject here with a question that we received from our webinar delegates. How can a watertight construction joint between the concrete soldier pile and shot create in retaining walls?
You're taking the rest of them, Gemma.
Yeah, sure.
So my interpretation of that question is it's a board pile wall with then shotcrete infill panels between. So I'd normally expect you've got a dowel connection between your board piles and your shotcrete. I'd see that that's probably acting as a pin connection, and I'll probably be concerned about the shrinkage of those panels against the wall. So I'd be pretty concerned about trying to rely on that in terms of a waterproof liner, or in terms of a waterproofing system. And I think if you looked at the British standards or Eurocode crack control requirements, I don't think you'd probably meet those. So I'd probably look at either like a contig wall solution where I'm grading between my piles, or a secant pile wall solution where they're interlocking, or a diaphragm wall, or if I was really going down the path of a board pile type solution separated, I'd probably look at some type of lining wall on the inside with continuous steel reinforcement to then provide that lining wall type system like Jarwood was alluding to before. So I think you'd be pushing pretty hard to get a detail for concrete panels to work as a watertight solution.
I just want to add, actually, the question is not very clear as to what's the brief of that, because it's a very generic question. But in terms of the structure integrity, or Chris mentioned crack control, but the fundamental part is you're going to do the part first, then you come back, put the panel in between. So there is a co-construction joint, let alone waterproof. There is no waterproof thing. I already mentioned, even put a membrane is not 100% guarantee. So again, I'll put the question back to whoever the person raised the question. So I suppose it's very important. You see, it's a question and answer. So when you raise a question, what the answer is expecting. That's all. Put it back in.
Thank you. Do we have another question from the audience? Thank you. This gentleman here, Nick. Oh, you probably do, just because of the webinar. Thank you.
Nicholas Haritos from Strucomp Proprietary Limited. My question is, water takes on different forms. It's a liquid when the temperatures are right, but it can become frozen when the temperatures are very low, below zero. What difference in your design approach do you take when you may have freezing and thawing occurring in your soil?
Thank you.
Okay. Well, I think that's a very good question. I suppose I'll start with a general statement that in Australia we're probably very fortunate that there were very few areas that we can have that situation realized. However, that I actually personally involved in some overseas projects. You do have to consider the change of temperature. So we look at two aspects. I think that the freezing and the thawing effects usually within limited depths. So when we deal with shorter retaining walls, and definitely that will be significant. But in general, if the say a shorter retaining wall, say within a few meters, and the water table is behind it, so if it's frozen, you're going to generate, because the volume going to increase as the water freeze, so you're going to have a huge pressure go against it. So actually push your wall. However, once you go beyond certain depths, say if I'm doing this wall, Bangkok is so hot, but in that situation, you still need to only look at the top few meters in that situation.
I guess my thought on that would be, I think it's kind of similar to a swelling soil or reactive clay, which might be a bit more typical to Melbourne, but yeah, it's an expansion there. So again, I'll be looking for a wall which can kind of take that ductile behaviour, so I'll be avoiding tie-back anchors into rock, because straight away it's just going to feel that tension, whereas something like these masonry segmental walls, they can tolerate that deformation and that movement while still performing adequately. So I think if that's a risk, I'll be looking at a more flexible type wall system.
We have got time for one more question. Gentleman at the back, thank you. So our speakers we'll have our drinks and networking after this, and our speakers will remain, so if you do have further questions.
Ross McEwen from Structural Edge Consulting Engineers. We've been noticing recently that the councils are starting to refuse to take groundwater, as are the sewer authorities. So the question becomes, what do you actually do with this water during construction and during the permanent state? Have you overcome that on recent projects, or it's got to go somewhere?
You go.
Yes, I've encountered that on some recent projects. We've still been managing to dispose of it in the temporary case during construction. Checking out the quality of the material and looking at the quantities coming through, so again, the chemical aspect of it. In the permanent solution, I think there may be more of a push towards permanent tank basements, potentially in the industry. So, yeah.
Is that realistic on a lot of these apartment developments? I mean, that's a much more expensive proposition, isn't it?
It is, that's right. So it's a change in the finances. So, yeah. yeah, it may mean that instead of going to a 3-level basement, you go to a 1-level basement. You know, you stay out of the groundwater table, or try to. Yeah.
I just want to add some of the sort of mostly adopted sort of basement development in Sydney. Sydney, probably from Melbourne sides, yeah, or sandstone, but it's not quite true. Some areas we do have like sands and clays. So the intention they're trying to do is for the perimeter wall. Actually, it's more like trying to minimize the water inflows. However, the basement, because if you cut off wall is deep enough, so that the hydraulic gradient, if you like, will be controlled such that you kind of course, semi-tanked system. So that will be a lot cheaper as compared to fully tanked solution. And that's very commonly adopted. However, for, I think, deeper than say 2 levels, people would consider fully tanked solution, because once you go more than 3 or 4 levels, it's just too difficult to deal with the cutoff.
I think there could be some change, like just building on from that, there could be some change in the industry in terms of construction methodologies. So I think on some of the large infrastructure projects, there may be some diaphragm wall rigs kind of coming down. So there'll be a bit more experience, that type of activity in Melbourne. So I think there may be more secant pile or diaphragm walls potentially coming out the market, but yeah, a lot more cost.
Yeah. Thank you.
Okay, thank you. Thank you very much. I'd like you to join me in thanking our speakers again. Thank you. In a couple of moments, I'll be inviting Greg Lowe, who's Austral's State Manager for Victoria, to come up here. But before I do so, I just wanted to thank you all for coming here tonight. I want to thank everybody on our webinar. It's just had an amazing response to this series. I also wanted to share with you at Engineers Australia, we partner with industry partners who are not only employers of engineers, but we believe are innovators, provide leadership in the industry, and support the profession as a whole. So I'd just like you to join me in thanking Austral. Thank you. So I'm going to invite Greg to close proceedings. As soon as we've finished, please join us, meet our speakers, have a drink, have something to eat, and enjoy networking as a team. Thank you again.
Welcome everybody. On my behalf and on obviously Austral Masonry's behalf and Brickworks, I would first like to thank the great speakers we had tonight. Well, their presentations were fantastic, and I'm sure you all agree. I'd also like to thank everybody for their attendance. The attendance is outstanding. We held one of these events 6 months ago?
No, November.
November, there you go, November. And again, the attendance to these events is just overwhelming. I'd also like to thank everybody on the web, obviously enjoying this tonight as well. And also I'd like to thank EA. Our partnership with EA has been phenomenal, and we hope to continue that. And overall, just like to thank everybody for attending tonight.
Thank you.
Thank you.
Thank you, Greg.
Thank you.
Thank you, and enjoy. Thank you very much. Well done. Thank you so much. Thank you, Mandy.
So we just put a sit back here. We practice here.